So, good afternoon. Um, so I hope people are doing pretty well. Today we're going to kind of finish up talking about the material for the course. I think that there's not too much more to say about the paired t-test. I'd like to give groups a chance to work on some things. So maybe right now, if you have a bit of extra time as I'm kind of talking through things, check to see on Blackboard that there are a couple of classroom handouts. I'll direct your attention to a couple of these a bit later today. Again, a couple of administrative announcements, just reminders, I guess, at this point. Remember that reading assignment 21 is due this Friday at 5 p.m. That's the last reading assignment that you'll do in the course. So I guess either you really enjoyed those, or maybe it comes as an enormous relief that now they're over. But either way, Friday is the last one that you'll work on in the course. Chapter 21 is the last. Is the last. It's the last chapter we'll talk about in an official sense. So the material that we're talking about now kind of represents an end to the course, though there may be some time to talk about some extra material, if the opportunity arises. There's a homework 12, which is due on Monday. That homework includes problems from both chapter 20 and chapter 21. I kind of felt bad that homework 11 didn't include anything from 20. So I put a couple of problems on there maybe to practice. And the main reason is that it's probably good to see these. You'll likely have to do some problems on the final exam so you want to get some experience sort of messing around with them a little bit first. So homework 12, due on Monday at 5 p.m. on my stat lab. This includes material from both 20 and 21. So don't be surprised if you see stuff on that homework which is related to the independent samples t-test. You should see that. And so when you're dealing with independent samples, either looking at differences of means or proportions, I feel like people probably should see at least a couple of practical examples of what you do, at least in the sense of looking at the homework. So it's due on Monday. There's no written assignment due next week. I think I finished grading most of written assignment 8. There may be a couple in there that I didn't check late yesterday afternoon. So my sense about that, I might wind up talking about it a bit more this week, maybe tomorrow or maybe Monday of next week. I'll put the solutions to written assignment 8 up toward the end of the week so you can kind of see where you stand on that. I made some comments. Overall, I think I'd say that written assignment 8 went much better than written assignment 7. So perhaps people are becoming comfortable with the idea of inference. It's good. Maybe it just required multiple exposures to it. So I feel kind of comfortable maybe thinking that. So, read the comments, see if you can make sense of them. And if you have questions about what I wrote, maybe send me an email and we can talk a bit more about them. Another general comment as we get closer to the end of the course. On Blackboard, you will see that there's a weighted total. It gives you your percentage grade out of 100. That I think is correct and up to date. Occasionally, I have to make sure that assignments are in the right category to get the weight to work out right. But this gives you your percentage. You can ask me questions about that if you want to in email. It's probably better to handle things that way if you have a question about the grade itself. I advise, just because you never really know how technology works, to confirm the grade as much as this is possible. If you look on the syllabus, there's a description of how the different components of the course are weighted, and you can kind of see what the components look like and apply the appropriate weights. You can always check this with Excel or by hand. I'll wind up looking at it again as well before I assign final grades. Final exam for the course will be. Let me look that. Now that I'm talking about it, let me look that up on the schedule. If you go to the syllabus and course information module on the Blackboard side for the course, if you bring up the spring 2021 schedule, you will see that there's a course schedule which sort of describes where we're at. We're actually a bit ahead of it. Next week, the week that starts April 19th, I think it's listed as being review for exam. April 26th is the last day of class. Final exam I have from Tuesday the 27th to Thursday, April 29th at 5 p.m. That covers roughly when you would take the final. Final, I think, is scheduled to be on April 29th, but I'll open it early. You can do it throughout that period. In fact, I'll probably open it up. I think 26 is technically a class day and we'll have class, but I might simply open the final exam up that morning and you can kind of see where it sits. So I think it says 27th to the 29th, but I might open it up so it's 26th to the 29th, just so you have that extra day if you happen to want to use it. So that's kind of where things sit right now. And, I guess we're sort of at the point of the course where you just want to go back, look at the grade, make sure you think everything is accounted for properly. One thing that happened periodically during the course of the semester, occasionally people would turn in blank documents for written assignments. If it happens that you got a 0 on a written assignment because you submitted a blank document, let me know. Presumably you had your intended submission on the computer, so we'll have to look into that. But if that happened to you, it would be noticeable, and I would have sort of reported as a comment that something was missed. If that happens, let me know. We'll see what's going on there. But again, just look at Blackboard, make sure you believe the grades are accounted for properly. It should be the case that my stat lab is reporting the grades to Blackboard directly. So you can always go back and check to make sure that the grades correspond. But right now, at least after Monday of next week, we basically have a complete version of the course modulo the final exam itself, which you'll take the following week. Any questions about this so far? So let's say, I think someone may have asked a question in chat. Right. Yeah, I have to account for a couple of more reading assignments, so stuff that you turned in, but I'll make sure and do that prior to the computation of the final grade, so everything's accounted for. And so that's right. So I guess wait, I'm asking another question. Okay, right. So and so again, just make sure everything you think is in order. If you think there's a discrepancy, you think you turned something in, but there's like a 0 there or something. That's mostly what I'm worried about at this point. And if you have any other particular questions about the grade or anything like that, you can always send me an email and we can talk. A couple notes. In general, when I assign grades for the course, there's a description of how the grade is convertible to a letter grade that you see on the syllabus. Be aware that the grade distribution will be no worse than that, meaning that that's a strange thing to say, but when you look at how the grades are distributed, what I generally do is I just sort of list the grades as percentage grades, and I kind of see where they stand and try to assign grades on the basis of how they make sense. And you use basically the syllabus as a guide for this. There's a description of 95 or better is an A or so forth. The truth is that, in that situation, what's probably true is it's going to be a bit less than 95 based on the grades. So it's fine if that's true. But what you see on the syllabus represents a worst case scenario. So the distribution will be no worse than that, I guess, from the point of view. Does that make sense to people? Yes, Grace.
Sorry if I'm just not getting this right, but when you say the distribution will be no worse, does that mean that hypothetically, if you get a 95, it'll be no worse than an A because that's what it correlates to on the.
That's right. Yeah, that's right.
Okay,
no worse. And so it's not. So I'm not. What I'm saying. So no worse can mean more than one thing depending on how you're thinking about it. One version of it would be, well, I got a 95, but somehow that translates into a B. That's not what I'm saying. So if you get a 95 in the course, that's going to be an A for the course, right? I mean, we know this right now. And so it's no worse than that. So it won't somehow translate to, it won't translate into a grade which is worse than what you see on the syllabus. Yes, Lily?
Wait, so an A is a 95 plus? Isn't an A usually 93 plus?
Yeah, usually. But what I'm saying is that if you look at that, it will be no worse than what you see. So the truth is that when I'm looking at the grade distribution for the course, my thinking is, looking at it right now, I'll probably stick, it just depends on what shakes out of the final. But, if you're looking at grades, I guess what I'm trying to say is, without saying too much, is that something like a 93 will probably be an A. It will probably convert into an A. But something like a 95 won't convert into anything less than an A, if that makes sense. Something like an 88 won't convert into anything less than a B plus or something like that. Does that make sense?
Yeah.
So it's not.
So you can only better then you can only do better based on the distribution.
That's right.
Sweet. Okay.
Yeah, and so, and that's typically what happens. I feel like I have to put something on the syllabus which serves as a guide as to how to convert the grades into something meaningful. But I mean, a letter grade I have to assign at some point on the basis of this percentage, but it will be not worse than what you see. Maybe it will be better, right? It depends on the ultimate distribution in the course, but it won't be worse than what you see. So it'll be I mean, that's a pretty conventional description of how grades are converted. But at the end of the course, I'll look at what people got overall, see how they did on the final, and make some judgment in the end about what makes the most sense. But it won't be worse than what you see there. So don't. I guess if you're thinking about an email to send me about the grade, you shouldn't stress out too much about what you see on the syllabus, as long as you've done the work along the way. Because again, I feel like people have done a fairly good job in the course. I'm pretty pleased with the outcome. If that makes sense. So does anyone have any other questions about this? Anything at all? Might as well ask. If there's something in the chat. Okay. All right. So with that said, yeah, again, just make sure everything's in order, make sure everything's accounted for. You'll want to check into it now, and then maybe give me a week to make sure that everything's actually in. So probably like today, I think it's the 14th, it's a Wednesday. So probably sometime late next week, we'll have a great picture of where things stand. Maybe you can use that weekend to kind of look at things, confirm that you feel like they're in the right place. And then take the final the following week. I think I'll probably have grades submitted for the course by early May, probably May 2nd or so. I think by statute, I kind of have to do that. So good. Today, the last bit of material, we were talking about paired data, so I'd like to continue that conversation. I want to go back to the example we were considering with the garage problem. So we have the data set for that, though I might have to reload it on the StatCrunch. But let me point out, what might make the most sense in this situation for the problem we're considering. Then we'll break people into groups and then see where things go from there. So, this is not quite what I want. That's the other handout from today. The handout I do want is this one. Here we go. So this is the problem we were kind of at. Yes, we were discussing yesterday. We were talking about inference for paired data. And the takeaway, I think, from the conversation is that what you're going to see in chapter 21 is really not very much different than a simple one sample t-test. That's really what it is. So either it's an estimate where the test statistic has some t-distribution, that's what's reasonable, or it's a confidence interval construction, which looks a lot like what you would do for means in some previous chapter. I guess it was 17 when that was last discussed. Except what you're looking for in these examples with these paired data is differences rather than the individual samples. So like in this example, you're looking at differentials, you're looking at some supposed differential in what a garage estimates, what one particular garage estimates for repairs for a car versus some other generic garage thinks is a reasonable estimate. And so the question is the garage that the insurer uses, this Jocko's garage, are you seeing estimates there which are systematically higher? So in order to try to figure this out, what we're going to do is we're going to take, let's say, 10 cars. And you have 10 cars, and you take a car and you take it to Jocko's garage. And Jocko, I guess, the proprietor of the institution, gives you an estimate for what it would take to get the car fixed. Then you take that same car and you take it to another garage and you get an estimate for whoever runs that garage. So these garages are you're keeping that other garage as the same garage, and you also have Jocko's garage to consider. So since the car is the same car that you're taking both to Jocko's garage and the other car and the other garage, it makes sense to consider the difference in estimates. So what you're sort of expecting to see is that somehow, if Jocko's garage is estimating that the repairs are more costly systematically, you're expecting that to happen on a car-by-car basis. So I think conceptually in a problem like this, it makes sense to think about the difference of estimates. And so when you look at the difference of estimates, the way that we might summarize the difference, these collection of differences, is through the mean. how does the mean difference behave? If the mean difference in this case is estimated to be greater than 0, then we might be able to conclude that we have evidence that Jocko is overcharging. And the other situation is maybe we don't have such evidence. And so when you're running, say, a one sample t-test, there are all sorts of different conditions to check. You usually want to imagine that the differences are independent. You usually want to imagine that the sample is drawn from some reasonably shaped population. And for that, you typically look at the histogram of the sample or something like this, or a QQ plot to see if it's normally distributed. And people tended to do that on written assignment 8 as an aside. They tend to handle that question pretty well. It's the same thing that you would have done in chapter 18. The process is more or less the same. But what you're really looking at is differences. And so, at least in this problem, conceptually, it makes sense to measure a difference, to look at paired data. Notice in this case, the two samples we get, the one from Jocko's garage and the one from the other garage, are most definitely not independent. You're dealing with paired data. And so the paired t-test is the way to go. Luckily, you can either do the paired t-test by hand, looking at differences, considering S, like in the formula for the test statistic, to come from the standard deviation of the differences. On the other hand, you can get StatCrunch to run it pretty quickly as well. So let me, you have the difference column, you're coming up with a confidence interval. So let's just see what happens when we do that. Oops, let's see what happens when we do that. So I hope I have the data, otherwise I'll have to find a way to find it. So when you go to data, we're gonna load the information from Jocko's garage and the research that people are doing here. So we load this from a file on my computer. I think it was in the download section. And it's right there. And when I load it, I get something that looks like this. So the way to interpret this information is as follows. The numbers that you see in the leftmost column represent the different cars. So you see that these numbers vary from 1 to 10. Each of these different numbers represents a different car. The number that you see in the next column is the estimate that Jocko would have given this private detective who was bringing the car in, or at least is working for the insurance company. These are the estimates Jocko is producing for each of these cars. And the other garage here, these are the estimates that the other garage is producing, but for the same car. For example, here on car 8, Jocko estimates that it would cost $3,600 to work out the repair. The other garage estimates at $3,380, so it looks like it's a positive difference. I went ahead on the spreadsheet and took the differences just so we could see what we were working with. If you look at the differences that's held in this, the difference between Jocko minus the other in that order is held right here in this column. And you see these differences are mostly positive. Sometimes they're negative, like right here, but mostly they're not. One time it's 0. So, what you're looking at is the difference. And the reason why that makes sense to do in this problem is because you're trying to see whether or not Jocko is systematically overcharging. It really makes sense to look at the gap between what Jocko wants to charge and what some other garage wants to charge, but for the same repair. And so the way that in this class we might organize these differences in a variety of ways. You can take these differences and you can construct a graph of them. For example, you can build a histogram of the differences. And if you do something like that, you get this picture right here. We can edit a bit further, even to include the mean, to kind of see where the average difference is supposed to be. And here the average difference looks like it's at about $114. So when you're thinking about this problem, the fact that the average difference is $114 does represent some evidence that Jocko's garage is systematically overcharging. But if we're thinking about this problem more carefully, we might want to look into working out an interval estimate for the differences. So it could be that that difference is positive, but it may be that it's simply because of the sample of cars that we're dealing with. So before I go on, does anyone have any questions about what we were looking at? Is this okay? So I feel like paired data makes sense in this case rather than independent sample, because the pairs are coming from in a sense you have one observation for each car within each sample. But it doesn't really make sense to think about observations associated with car 1 and car 2 to be independent somehow of each other. So if we're working on an interval estimate, luckily you can get StatCrunch to do it. I'm not sure that I want to do it by hand. You know, you can read a little bit about the formulas in the text if you really want to work out things by hand using Excel. I don't mind if people do that. I actually saw a couple of examples of this on a written assignment where people wrote it down. That's good too. You know, it's nice to be able to do that sometimes, but we can use StatCrunch to do it. So if we want to come up with a 95% confidence interval, remember that what we're doing is we're trying to come up with a plausible range of values for the true difference. And so the difference in this case is this paired difference, where we're looking at the difference between the difference that's associated on a car-wise basis. We only have 10 cars. There are some problems with this method. It's reasonable to criticize what we're doing. There are several reasons why you might want to be a little critical of it. One reason is if we're trying to do inference on the differences, the histogram that you just saw is not really normal. It's not terribly normal in appearance, it's sort of flat, right? It looks kind of like a uniform distribution. So you might wonder a little bit about whether or not the methods are entirely appropriate. But at least it looks kind of semi-unimodal, right? Like it looks like the typical observation is about 114. That's where the peak of the distribution is. So maybe it's not that unreasonable, but you should be a little cautious. You know, other concerns that you might have about this from a practical point of view, when you're drawing the 10 cars, you know, are you choosing the 10 cars at random? It may be that for whatever reason, for certain types of repairs, Jocko charges more than the other garage, but for other types of repairs, maybe it's the reverse. So it's sort of hard to say, you know, whether or not this analysis is perfect. There are ways to criticize it, I think. There are reasonable criticisms that you could use. I don't think that it's like binding. You know, it just kind of gives you an idea of what's going on. It gives you an idea of what the evidence looks like. But of course, you know, if you're trying to like sue Jocko for fraud or something like this, or hold Jocko liable in criminal court, you're going to need much more than what we're doing. There would have to be, I think, much stronger evidence to hold this person accountable if, in fact, you know, there was any fraud going on at all. But, you know, it gives you an idea of how things look. Anyway, if you want to actually construct a confidence interval, you would go to the stat t-statistic, because that's what's essentially you're trying to do. And you're looking at the paired t-statistic. Now, StatCrunch, when it does this, it wants you to subtract in a certain order. It sort of writes this down right here. Mu of the difference is mu1 minus mu2. That's the inference you're trying to do. You want a confidence interval. So we will subtract in the order in which the columns appear. Column 1, we'll look at Jocko. We don't care about car. Column 2, we'll take other. And we try to construct the confidence interval. You can kind of construct. You can build a histogram and the summary statistics if you want to. Kind of already looked at that, but what does the 95% confidence interval look like? It looks a bit like this. Here, the lower confidence limit is on the order of about $32. The upper confidence limit is about $195. So, you know, the degrees of freedom is 9, which is not that large. And the standard error is pretty big. So, you know, if you increase the level of confidence, you could probably, you know, convince yourself that nothing was going on. If you believe that you need like a 99% or 99.7% level of confidence, you would actually get 0 that way. But, you know, if you're just looking at a 95% confidence interval, what it looks like this is saying is that there at least is some evidence that Jocko systematically overcharges, because the mean difference, a plausible range of values for the mean difference between Jocko and the other garage on a car-wise basis lies between $32 and $195. So, you know, you can kind of get StatCrunch to do the calculation. There are all sorts of interpretations. You know, I don't know that this is terribly ironclad. You know, you can't sue the guy for this, but, you know, you would wonder a little bit about it. But maybe $32, you know, when you're talking about thousands of dollars worth of repairs, probably not that much. So maybe you're not that concerned about it. So maybe the issue is effect size, you know, it's less of a concern, or maybe you think it's just an idiosyncratic issue where you're looking at these 10 cars, but if you take a different group of 10 cars, maybe it looks different. So, you know, probably more work needs to be done in this kind of situation. Maybe more cars need to be studied, but at some point Jocko would probably get suspicious if you kept bringing these cars back. So do you have any questions about this so far? If you're working for the insurance company, I guess what you would say is you might think at minimum Jocko was overcharging at a rate of about $32 per car. So if you're trying to recover money from Jocko and you've sent 75,000 cars his way, you know, that gives you an idea of what you're trying to recoup. minimally, it's whatever 32 times some large number of cars is. I mean, that's one way of interpreting what you're thinking about here. In any way, that's the idea. Yes, Lily.
I just have a clarification question because I cut out for a second. So how did you get that 34? Like, where did you pull that from?
The 32 or the 34?
How much he's overcharging by?
It comes from the confidence interval estimate. So let me go back.
Is it like one of the things, or like what's in it? Like where?
So what do you, let me pull it up and I'll show you. I'll try to show you what I mean, and maybe you can ask again. So when you look at the display, what you're seeing is a lower confidence limit of about $32, an upper limit of about 195. And so what that confidence interval represents is that it's an interval estimate for the car-wise difference in price of the repair. So for the average of those things, I guess is what I'm saying. So when you take a look at what we have here, the 160, the 250, the various other numbers you see, let me move this over so it's a little easier to see. The various numbers that you see here are all differences that are taken on a car by car basis in a certain direction. You're taking what Jocko estimates minus what the other garage estimate, and you get these numbers. So the confidence interval estimate here is a confidence interval estimate for the mean of all possible differences. And you were using the sample of 10 cars in order to come up with the interval. And so when you look at 32 to 195, what you're saying is this: I don't really know exactly what, or I don't know exactly what Jocko is overcharging on average, but it is reasonable to think that the overcharge is between $32 and $195 per car. Does that make sense?
Yeah, it does. Thank you.
And so that's the way that you want to think about that interval. I think so that's a productive way of thinking about that interval. You can think about it if you want to try to sue Jocko. If you take 1,000 cars to Jocko, you feel like you've at minimum have been overcharged by about 32 grand, and the insurance has to like pay that out. So there may be a reason to want to know this information. I would say that a problem like this is sort of an entry point into this kind of work. If you're trying to come up with some way of suing people for what you think has been overcharged, you probably want to be a little more careful than this in trying to assign, a numerical value to damages. But I feel like, in civil cases, this is often the case where people try to assign some numerical value to damage. This is an example of that, which is actually pretty concrete, because at least you feel like it comes from cars that you're taking to junk. But there are ways to criticize it. It's not perfect. Maybe it's reasonable. So with that in mind, I'd like I'm going to break people into groups in just a second. Hang on. Let me show you what I'd like people to do. There was a handout that we worked on a little bit yesterday but I think yesterday we were simply trying to classify the data as being paired or not. Let me while I'm here, let me break people into groups, but maybe 4 to 5. I'd like people to consider. So in that same handout, there was a problem that we didn't do, and that was problem 1. What I'd like people to do in groups. So we'll take a few minutes to do this. I'll undo that in just a second. Is problem 1. Pay particular attention to A when you read through the problem. Think about what the hypotheses are, and this will sort of tell you how to do the test. And then, maybe perform the test. May take a little while to find the data set. So think a little bit about A through C. Is there something wrong with my pad at the end of the semester? I hope not. We'll think as groups about questions A through C, then we'll formulate the hypothesis and think about these things a bit. Think about the results we got. I'd like to leave D for sort of a more general discussion in just a second. Notice that the data set is associated to my lab. I feel like I have to kind of explain how you might get there. So let me just as a reminder, let me me open up. Let me open up my version of it, and I'll explain where this comes from. So to find the data set that you want, we did this earlier in the semester, and it was like a total disaster at the time, but we'll try it again now that everyone has access to StatCrunch. Where you should look for the data set is on the left-hand column. I'm hoping that there's sort of a StatCrunch button right there. When you open it, you can find data sets from the text. Data set that you want is in here. You're looking at, let's see, which is it? Friday the 13th traffic. So if you want to bring that up, you would just go here, and the data set would preload into StatCrunch, and it would tell you a little bit about what say the traffic looked like on the 2 consecutive Fridays. And so when you're thinking about this problem, this is the data set that you're going to use. You don't really have a lot of information. It's 1 through 10, not a lot of observations. So maybe that's an issue. But when you're thinking about it, that's the data set that you want to use. So does anyone have any questions about this right now? That's where you look for it. Now, what I'll do, so that you have people in rooms, it's about 127. Take a few minutes, might take a minute or two to load the data, and find it and think about the results. But try A through C, I think, on that handout on Blackboard. Right now about 127. Let's meet again at 137, and then we'll have a more general discussion of this. And then we'll finish up, I think, with a discussion of part D, and that's probably enough for today. Let me open the rooms. So you should have your invitation. Yeah.
Professor, I never got the invitation to enter a Zoom breakout room.
Let me send you to one. Yeah, it looks like you have not been assigned. So let me put you in room 2.
Thank you.
Yep. Okay, welcome back. Let me go to this page right here. I'd like to write a couple of things down, maybe before, just, for the purposes of explaining the notation. When formulating, this may be an issue, may come up in the problem. When formulating, the null alternative hypotheses, you typically use, it is typical to use a symbol mu sub d to represent the mean of the differences. So when you're doing inferences like we're about to do, that maybe is the symbol that you would use. And when you're thinking about d being a difference, the order of subtraction matters. So you have to be careful. You have to be clear in your own mind. Be clear in your own mind about the order of subtraction. And this happened a couple times in the unpaired example in written assignment 8, I think it is. There was some confusion about the direction of the subtraction. People subtracted one or the other way. Mostly the confusion didn't happen. I think people did a pretty good job, but occasionally there was an issue. So when you're dealing with this particular problem, you see that you have a published article is Friday the 13th bad for your health. Researchers in Britain examined how Friday the 13th affects human behavior. One question was whether or not people tend to stay home more on Friday the 13th. So the data set that you're seeing looks like the number of cars passing through a particular junction on the M25 motorway for consecutive Fridays at five different periods. So let's see, what it is that we actually have. So in July, you have that versus that, you have that versus that at two different junctions. So you have junction 9, junction 10, junction 9, junction 10, repeated, kind of consistently. And then you have the data for Friday the 6th. That's what this are. And this is a count of cars passing through a junction at a particular time. Same thing for Friday the 13th, the next Friday. And so when you're thinking about this problem, I guess you are thinking about doing some sort of paired data analysis. And so what are really the pairs? It's like for each junction and day, for each junction and in some sense observation, you have a pair of numbers. You have a number coming from the 6th and a number coming from the 13th, yes? And you're trying to compare, or you're looking at the pairwise difference. So if you compare the 6th and the 13th in 1990 in July at junction 9, if you subtract the 13th from the 6th, you get something on the order maybe of about 700 cars. And you're kind of doing the same thing for each of these. So before I go on, does everyone see what I'm saying? Makes sense to think about this as being paired data. You're looking at the pairwise difference at particular junctions of number of cars passing through that particular junction. One observation is made on the 6th and the other the 13th for various different Friday the 13th. Yes, Lily?
So are you subtracting the 6th and the 13th from each other, or are you subtracting the junctions?
You're subtracting the 6th from the, yeah, right. The direction of the subtraction is in the 6th. You're comparing the 6th to the 13th. So I guess in answer to your question, the order of the difference is the observation on the 6th minus the observation on the 13th. So you're not comparing things junction-wise. I know what you. So you're not. I mean, I know what you mean. You're not looking at the difference between junction 9 and junction 10. You're viewing 9 and 10 as two different junctions that you have some data about, and you're comparing what's going on the 6th and the 13th. So the order of subtraction is 6th minus 13th.
So then from there, are you, like, if you were to do another column of the differences, do you have like the differences for one of the junctions, and then differences for another one of the junctions, or are you just doing it all in the same column?
I don't. So I'll bring it back. So if you had a column of differences, say that column was like right here, the number that you would expect right here would be that minus that, and that would be the information coming from junction 9. Does that make sense?
Yeah, it does. But I guess what I'm wondering is like, when you're looking at the mean of the differences, are you comparing the two junctions? So you have to separate those.
No,
out,
I'm
right?
putting them all together. So
Okay.
basically, so I'm not looking at means junction wise. Maybe that's what you're asking.
Okay. So it
Yeah,
doesn't
so-
really matter like what the junction is then.
Yeah, no, it's just, I
Okay.
mean, it may matter a little bit, right? When you get into trying to deal with whether or not you think these methods are appropriate to analyze this problem, there probably is a question about it. You know, you have information about 9 and 10, but what makes those junctions so special, right? Aren't there others that you would be interested in? Aren't there other places where you would try to do this sort of estimation? You know, why were these chosen? You know, were the junctions chosen at random? I mean, the days weren't, right? I mean, you know that you have to, if you're dealing with Friday the 13th and the previous Friday, you know what you have to pick in different years. But it's weird, right? Like if you look at it, I think it's kind of a weird analysis, in my opinion. I mean, you can do the analysis, but it feels strange because you're only looking at junctions 9 and 10 on this highway. You know, why not look at others? Or if you look at all possible junctions on the highway that you're talking about, you know, you're clearly not randomly choosing 9 and 10 every time out of it. So, you know, there's a looseness to the analysis, I feel, for this reason. We have it, but you know, I question it a little bit. You know, it would be something that, you know, it's a concern. Like, does that make sense? You'd worry about the randomization condition here. You also kind of worried a little bit about the independence condition because you wonder, you know, yeah, I mean, you wonder basically how many junctions are there to study, right? Like you've looked at 2 of them. Is that all that there are? Are there, you know, you have junctions 9 and 10, so presumably you have other ones, but why weren't those looked at? Is it because, you know, at these junctions you happen to have, you know, a large number of cars passing through that you can look at? It's weird to me. It's weird to me. But you know, that weirdness is sort of more associated to what you would want to look at, I think, in part D, when you're trying to analyze or criticize the conclusions. And I think it's always fair to do that. Like when you're looking at the methods, you can easily use StatCrunch to come up with an interval estimate that you might think is reasonable. But how seriously should you take the result? I mean, you know, if there are some serious methodological flaws, then maybe not that seriously. So it's a question. You know, it's sort of some of the stuff that you have to look for when you're thinking about whether or not certain assumptions are met, to use, you know, certain modeling assumptions are met, I guess I would say. If you go back to, okay, whoops, I didn't mean to cut that off, sorry. When you go back to the problem, it's asking you to, you know, before you really do anything, you know, they're paired. And, you know, you're looking at, I mean, and this is because you were looking at data, and I'll put samples in quotes because I'm suspicious, generated from the 6th and 13th. So it's a bit like Jocko's Garage where you have the one car, right? It's like you have junction 9, you have junction 10, you're looking at the 6th and the 13th, but it's like those 2 junctions are contributing some information on the 6th, but maybe possibly different information on the 13th. So, you know, if a junction 9 is busy in a particular way, the observation on the 6th and the 13th certainly won't be independent. They'll be related, they'll be paired. So paired t-test is the way to approach it if you approach it at all. Using the notation, I guess the theory here might be what? If you take the difference between the 6th and the 13th, it seems like the authors of the piece want to think about whether or not there's evidence for the average difference being positive. Like, and the difference is the direction. I'm going to abuse notation a little bit here just to give you an idea of what I'm trying to say. But D, I'll put it in quotes because it's not really saying it's a subtraction, but D is like the 6th minus the 13th, if that makes sense, the 2 consecutive Fridays in that order. And so if you take a look at the average difference, you're sort of wondering about the alternative, you know, if there's evidence against the belief that there basically is no difference. And so I think that's probably a pretty reasonable approach if you believe inference can be used at all in this case. If you want to run the one sample t-test, you would use StatCrunch to treat it as paired data. So you go to stat, t-stat, paired data. The one column, the first column you'd use, I guess, is the 6th. That's the thing that makes the most sense, I think, in context. And the 13th will subtract in that order. We're looking for evidence of a difference in a particular direction based, I mean, it's sort of suggested by the write-up to the problem. If you test for a difference, you're not expecting the difference to go the other way, mainly because you think that, I mean, the supposition is largely that people view Friday the 13th as being an unlucky day. So they're liable to stay home out of some, you know, fear that they might be in an auto accident or something else bad may happen to them. So, you know, if you have or are doing the hypothesis test, you know, we're not really told very much about we're not told very much about like the significance level. We can make our own judgment in just a second. Like the problem suggests, let's look at a QQ plot of the sample. So when you hit compute, you're looking at a QQ plot of the difference. What you're seeing here when you're running the test is you see a rather large test statistic realization. You see something on the order of about 4.93. Even with 9 degrees of freedom, the p-value is pretty small. So p-value here, of course, is the probability of getting a realization like 4.93, at least as extreme as 4.93, under the null hypothesis that you see up there. Pretty low number. In a sense, the class almost trains you to reject the null hypothesis when you get this type of information. QQ plot is included. It's actually pretty sparse. You really only have 10 rows, so you have 10 dots, but they do seem to be arranged in kind of a linear fashion. So at least the sample of differences looks normal. The dots that you're seeing here are associated to differences rather than, you know, the individual samples. One thing that you can also do, let me edit it. You can include a QQ plot, but you can also, you know, look at a histogram and you know, when you compute, you get one extra screen to look at. You know, the histogram actually looks kind of okay. Like if you look at the differences, obviously the mean, the sample mean is very much positive. It's on the order of about 1800 or so. But you get kind of a nice symmetric unimodal diagram. This is kind of the thing you're looking for. QQ plot basically is telling you the same information. The sample looks okay, looks basically normal. You know, there's some weird thing up here, down here, but that's not unusual for this type of thing. So, you know, at least that part's okay. So, you know, if you're doing the work here, or if you're writing down, you know, what the conclusion is supposed to be, the value of the test statistic, so I'll just write this as t-stat, it's about 4.93, p-value pretty low, 0.0004. So at alpha equal to 0.1, we inject h sub 0. So we think that there is evidence that people behave in some unusual way on Friday the 13th. I'd like to take a moment to kind of criticize the example. I feel like the mathematical conditions are okay. So the pure mathematics, if you're looking at the diagram, if you're only looking at either the QQ plot or the histogram, I think you feel okay about what you're doing. The sample is a little small. So I guess n isn't big, but at least the sample of differences looks reasonably normally distributed. I feel like the criticism, I feel like both the randomization and you know, independence might be a problem. And I guess the reason I think that is, I mean, how many junctions do you actually have to look at, right? Like, what if there are 100? Well, maybe you feel better about it. But what's the chance that if you select a bunch of junctions to study and you only get 9 and 10 repeatedly, that's probably not going to happen. So you actually don't feel like these observations are chosen randomly from some sort of universe of possible observations. And I think that's actually the biggest criticism of this project. It's not clear that you should take the results. You should take them with worth a grain of salt, right? If you're just measuring differences, how is it that when you look at sort of random selections, you only get these 10? You know, it feels wrong somehow. And so it's worth criticizing. We have the estimate. We feel like there's a difference. But certainly you would want to go back and think about whether or not there's more in the paper worth considering than, you know, what's just in the write-up. So it's okay to criticize stuff. It's fine. You should feel free to do that. And lots of times, I guess I would probably end with this type of warning. When you're looking at the statistical work that you're doing, it's often not the mathematics of the situation which will betray you. It's the other stuff. It's the stuff about how the data was gathered, how the data is processed in some way, how the data is analyzed. It's just countless decisions that researchers want to make when producing a paper. That's where you're liable to get the most variability in this type of work. It's usually not in the mathematics. So always be aware of that. You know, those are always things to look into. When you're thinking about a result, there's no need to accept it uncritically. You know, always going back and thinking about whether or not, you know, when you read what someone is actually doing, whether or not you believe that the work they're doing, you know, is plausible or reasonable to you. Whether or not you feel like the data, you know, like in this case, you feel like the data is randomly gathered. Whether or not you feel like it's a big enough sample. Whether or not you feel like, you know, the population, you might have certain beliefs that it's normally distributed with respect to the characteristics that you're looking at or not. All those things are worth considering. Design of experiment, very, very important. Design of survey, very important. That's usually where the devil can be found. So I guess I'll probably leave it at that. And I guess this sort of represents kind of the end of the line. This today is, I think, the last major bit of material we'll cover. So I'll see